Hi everyone. In the previous lectures, we finished our discussion of the frequency response of single stage MOS amplifiers. We saw what is the effect of parasitic capacitors on the gain of a single stage amplifier. We saw how the parasitic capacitors makes the circuit deviate from its ideal behavior. We saw how amplifiers start losing their amplifying abilities and they turn into passive circuits for in case of a common drain amplifier. They lose the ability to, an ideal amplifier should be able to give a good power gain. We saw how does, for example, a common drain amplifier loses its ability to give a power gain because of at very high frequencies because of the parasitic capacitors. Now naturally the next step in our analysis is to understand the frequency response of differential amplifiers. Now, if you recall from our discussions on differential amplifiers, we said for any differential amplifier, we can draw an axis of symmetry around which the differential circuit will look like a perfect mirror image of each other. And also we argued because of that, we can reduce a differential amplifier to an equivalent single-ended amplifier called as a differential half circuit. And we said by analyzing that single-ended amplifier, we can gain all the information that you need to gain for a differential amplifier. So by that logic, I might argue that we have already carried out an analysis of differential amplifiers as well. Since we have finished the frequency response of single-ended amplifiers, we have also, in effect, have carried out the analysis or at least developed the basics necessary to understand the frequency response of differential pairs. So that's what I've shown here. A differential amplifier can be seen as two single-ended amplifiers with inputs, differential inputs fed to them, and the outputs, the differential output is the difference between the two outputs. Now we have already analyzed how to find the frequency response of single-stage amplifiers, single-ended amplifiers. Now all we need to do is to apply those results and try to understand a differential amplifier as well. Now in case of a single-ended amplifier, the main parameter of interest that we were looking at when we were analyzing single-ended amplifiers was just the single-ended voltage gain itself. We were interested in understanding what is the value of A of S, which is the voltage gain of a single-ended amplifier, and we saw how it varies as a function of frequency. And we said that's very important for a design engineer to know, because then you will know what are the frequencies that you can apply, what are the signals that you can apply to an amplifier for faithful amplification. But now in case of differential amplifiers, we defined nearly four important parameters which characterizes gain in a differential pair. The first one of them is what we call the differential mode gain. This is the actual gain of interest in a differential amplifier. It's nothing but the differential output. So you measure the output differentially. Here it is VO plus minus VO minus, and divided by the differential input. So input is fed differentially, output is taken differentially. The ratio of the two, the output differential voltage by the input differential voltage, is called ADM, or the differential mode gain. The second gain of interest is ACM. So we saw how a differential amplifier responds to common mode inputs, which is I'm going to short both the inputs and apply the same input and see how the differential amplifier responds to this. First, we will measure the common mode output. So we will short both the outputs or take the average of the two outputs. So here it is VO plus VO minus by 2 divided by VICM. So the common mode output change in the common mode output divided by the change in the common mode input is what we refer to as ACM, or the common mode gain. And the third quantity of interest we discussed was ACM-DM. We said ACM-DM, or differential mode gain for common mode inputs, is a measure of how symmetric the circuit is. For a purely symmetric circuit, if you apply same inputs for both the inputs, then both the outputs will change by the same amount. Whether they both can increase or decrease, but the change is going to be the same. So keeping that in mind, we can say ACM-DM will be 0. So that's nothing but change in the output. The output will be measured differentially, VO plus VO minus, divided by VICM. This we called it as ACMDM. So for a perfectly symmetric differential pair without any mismatches, ACMDM was exactly equal to 0. But then we argued any differential amplifier can be represented, the gain of any differential amplifier can be represented as a product of short circuit transconductance GM times the output impedance R out. So these are both DC values. Now if a differential amplifier exhibits, or if there is any asymmetry or mismatch in a differential amplifier, then when we draw the differential half circuits and compute the short circuit transconductance and output for each half of the circuit, they both will not be exactly the same. So let delta GM be the error. Delta GM be the error in transconductance between the two halves of the differential circuit, and delta R out be the error in output impedance between the two halves of the differential circuit. Then the ratio delta GM by GM is what we called as the fractional error in transconductance, and delta R out by R out is what we called as fractional error in output resistance. We said ACMDM, the differential mode gain for common mode input, can be expressed in terms of ACM of S. So this is a result I've already discussed in when we were discussing differential pairs. You can go through that and refresh your memory. It can be expressed as fractional error in transconductance and output resistance times ACM of S. ACM here is the common mode gain. I am going to call this term delta GM by GM plus delta R out by R out as E. So this is called as the error. So this error here is the fractional error because of asymmetries or mismatches between the two halves of the circuit. So error will obviously be a number always less than 1 and very close to 0. So I am going to represent mod of E to just say that it's always a positive quantity. Positive quantity, but it is less than 1. So ACMDM, the differential mode gain for common mode inputs, can be represented as a product of error, the fractional error because of asymmetries, times ACM, the common mode gain. And the fourth more important parameter which we discussed for a differential amplifier is CMRR, the common mode rejection ratio. That we said can be seen as the signal gain. This is your actual signal gain of interest. This is the differential signal gain divided by the common mode signals gain. See here both the gains are for differential outputs, but the first gain here, ADM, is for differential input. This gain here is for common mode input. So we can say that ACM in a differential system, a common mode signal can be seen as noise. So this is ADM is signal gain. This is actual signal gain divided by noise gain. So we saw that this is like the ratio of signal to noise gain, and we defined that as CMRR. And ideally we said for a perfectly symmetric circuit, since ACMDM will be 0, CMRR should be infinity. For ideally it should be infinity. But now we will see that's not the case, and in that case how does how does CMRR change with frequency? Now what we have discussed so far is we have listed out what are the important gain parameters: ADM, ACM, ACMDM and CMRR. These are the 4 important parameters in a differential pair. What we will be seeing in this lecture is how does all these 4 important parameters change as a function of frequency. That's what we will be mainly dealing with. We will see how all these parameters change as a function of frequency. Now finally, CMRR can also be expressed in simpler ways. So ACMDM, I am going to represent ACMDM as mod of E times ACM of S. So CMRR can be written as the ratio of differential mode gain ADM of S divided by E times ACM of S, ACM being the common mode gain. So we can observe a very interesting property here. If you have the poles and zeros of ADM of S, the poles and zeros of ADM of S will also be poles and zeros of CMRR of S. So if CMRR, common mode rejection, I am going to plot it as a function of frequency, then we can, by looking at this equation, we can say the poles and zeros of ADM of S will also be the poles and zeros of CMRR of S. and the poles and zeros of a CM of S, the common mode gain, will be the zeros and poles of CMRR of S. And we can also express them, since we will be plotting all our voltage gain and everything in terms of in a Bode plot. So I can substitute S equal to j omega, I get the frequency response. I'll take 20 log of CMR of omega, can be written as a dm of 20 log of a dm of omega minus 20 log of a cm of omega minus 20 log of mod e. Now this term minus 20 log mod e will always be positive because e is less than 1. So log of e will be a negative quantity, and minus of that will be always a positive quantity. So to get CMRR in the frequency response of the common mode rejection ratio, all you need to do is first plot the differential mode gain, the Bode plot for it, and then plot the common mode gain and subtract the two, take the difference between the two, ADM minus ACM in decibels, and then add this term minus 20 log of E. So minus 20 log of E will be a positive quantity, we'll have to add it, then we get CMRR. So this is what we are going to do. We'll take a set of circuits, differential amplifier circuits, and then we will analyze and see how all these parameters look like. Before we go into the analysis of all these parameters, I just want to quickly refresh your memory about a circuit which we had already discussed when we were discussing frequency response of common source amplifiers. The circuit shown here is a common source amplifier with source degeneration. So I have a source degeneration with a capacitive load, capacitive source degeneration, and also a load also has a capacitance and a resistive component. I have already derived how to solve this circuit intuitively. I'll just very quickly take you through both a rigorous analysis and also an intuitive approach to find poles and zeros for the circuit. This is very important. We will see that most of the differential pairs, if you understood this circuit, then more or less we have understood most of the differential circuit analysis as well. The voltage gain of this circuit, I am going to call this impedance as Zs of S, this impedance as ZL of S, can be written as Gm by 1 plus Gm Zs of S. So this is your short circuit transconductance for the circuit. If you short circuit this node and measure the transconductance, you will get Gm by 1 plus Gm Zs. So I said this happens because of source degeneration. There is some kind of feedback. So your Gm becomes Gm by 1 plus Gm Zs. And the output times the output impedance ZL of S. So there will be a minus sign here because it's a common source amplifier. Now if I substitute Zs of S, which is the parallel of Rs into Cs, as Rs by 1 plus S Cs Rs, and ZL of S as RL by 1 plus SCL RL, I'll get this expression. So I'll get minus of GMRL by 1 plus GMRL RS, this is your DC gain, times the zeros and poles, the product of zeros and poles. So here the numerator shows 0, 1 plus S CS RS, so the 0 here is 1 by RS CS is a 0, this is a left of plane 0, and we have two poles here. 1 plus SCLRL is the output pole, so 1 by RLCL is the pole, and we have a third pole which is at 1 by CS into RS parallel 1 by GM. Now throughout this lecture I am going to make this assumption RS is much greater than 1 by GM, which means this expression RS parallel 1 by GM can be approximated as 1 by GM. So the pole can be written as GM by CS. So we have three poles, two zeros. So 0 is at 1 by RSCS. We have a pole at GM by CS, and we have another pole at 1 by RLCL. So these are two poles and 1 0 in the system. I'll very quickly take you through how did we analyze the circuit intuitively. Intuitively we said first find out the short circuit transconductance and then multiply it by the output impedance. So for short circuit transconductance, the circuit reduces to something of this format, in this form. So the output is short circuited here. So we'll have to find the short circuit transconductance for this circuit. Now to find the short circuit transconductance, we have one capacitor here, which means at max you can have one pole and 1 0. So we already discussed that if the number of poles, the maximum number of poles and zeros in any system will typically be equal to or less than the number of capacitors. Less than or equal to the number of capacitors. So here at max you can expect one pole and 1 0 in the circuit. So here the condition for 0 occurs if your source impedance is open. If this impedance acts like an open circuit at some value of S, then the current becomes flowing through this will become 0 because there is no path for the current to flow. So the value it becomes, the frequency at which or value of S for which it becomes infinity is that we have already discussed. We have a parallel RC circuit. When RS becomes equal to minus 1 by SCS, you get this impedance blows up to infinity. From that we get the 0 as minus 1 by RSCS. So this is in S plane. So we said the value of omega will be 1 by RSCS radians per second. That's how we calculated the 0. And to calculate the pole, what we said was that we'll just take this term, the effective transconductance, Gm by 1 plus Gm, and equate it to infinity, or denominator to 0. So 1 plus Gm of S, we will equate it to 0. We will get Z of S minus 1 by Gm. And by solving this, substitute Z of S, this is Zs of S as Rs parallel 1 by SCS. We will get this expression for the second pole as 1 by Cs into Rs parallel 1 by Gm. Now this is I'll just briefly talk about the time constant procedure. So whenever you have for single pole systems, especially if you have single pole non-interacting capacitors, I'll talk briefly about what is non-interacting capacitors in the next lectures. So then I can use a very simple approach to find the poles in the circuit. All I need to do is that to find the time constant associated with each capacitance. So let's say I have this capacitance Cs. All I need to do is find out the equivalent resistance seen by the capacitance. So I can remove this capacitance and find the equivalent resistance seen at this node. That will be Rs in parallel with 1 by Gm. So Cs times this impedance Rs parallel 1 by Gm will give us the time constant associated with this capacitance. Then the pole is simply given by the inverse of this. 1 by this term will give us the pole. So this can be applied if you typically have, especially for a single capacitor system, you can easily apply that. When you have many capacitors, we can apply it even there, but we have to exercise some care. I'll talk about that in the upcoming lectures. Probably towards the end of the course, I'll discuss that. So we saw how to find the pole here. The pole, I said, if you assume Rs to be much greater than 1 by Gm, this can be approximated to Gm by Cs. So this circuit we saw there is one pole 1 0 because of one capacitance. At max you can have one pole 1 0, and we saw both the values. 0 is at 1 by RSCS and pole is at Gm by Cs. You can directly see here that if Rs is much greater than 1 by Gm, I can say that the 0 will occur much before the pole here. So the 0 will occur first and pole at a later frequency. Next we will find the poles and zeros because of the output impedance here. So the output impedance in the circuit, you short circuit the input and measure the impedance near the output terminal. So the impedance looking down will be infinity because R0, I have assumed R0 as infinity. So even though you change your drain node voltage, there will be no change in the current through the MOSFET. So I can completely ignore the MOSFET and this circuit. I am left with only the parallel RLCL circuit. Now in this impedance again you have one capacitance, so therefore you can argue that at max you can have one pole 1 0. So first quickly we'll estimate 0. To estimate 0 you'll have to find the frequency at which the impedance goes to 0. That will happen since you have two elements in parallel. If any one element goes to 0 at some value of S or omega, then the impedance goes to 0. Here since it's a capacitor, it will go to impedance will go to infinity. Impedance will go to 0 at S equal to infinity or omega equal to infinity. So the 0 in the circuit occurs at infinite frequency. So since it's not a finite frequency, I'll ignore that. The next problem is to find the pole. To find the pole, we want to see the condition where this impedance blows up to infinity. So that will happen when RL equals minus 1 by SCL. So the pole will be a minus 1 by RLCL. This is a left of plane pole. So in terms of radians per second, I have written it as omega P1 as 1 by RLCL. Now we should be able to plot the Bode plot for this system. So I'll quickly write the frequency response. So we have a common source amplifier with source degeneration. So Rs and Cs are the source resistance and capacitance. RL and CL are the load capacitance and resistance. So we are supposed to find the voltage gain for the circuit, the Bode plot for the circuit. So first we'll write the DC gain, which is the short circuit transconductance at DC, which is GM by 1 plus GMRS times RL, which will be your DC gain. Then we calculated the poles and zeros. We saw there is only one zero in the system, other zero is at infinity. So I'll write 1 plus S CSRS. And we saw there are two poles in the system. The first pole, because of this, the short circuit transconductance was approximately at GM by CS. So I'll write 1 plus S CS by GM times 1 plus S CLRL. 1 by RL CL was the second pole. So we can write this expression this way. So again, I've already discussed how to write the transfer functions. So 1 plus S by omega Z1 divided by 1 plus S by omega P1 into 1 plus S by omega P2. So if you know the DC gain and the zeros and poles, you can write transfer function for any circuit. So I just substituted the values of omega P1, omega P2 and omega Z1 here. I get this expression. Now we'll make some assumptions before we go ahead with the Bode plot. So first we need to understand what are the values of zeros and poles, and so that it will be easier for us to plot. The 0 occurs at 1 by RSCS. Then your pole will occur at 1 at GM by CS. So since I said GM RS is much greater than 1, or RS is much greater than 1 by GM, 1 by RS will be much smaller compared to GM. So the 0 will occur first, then you will get the pole. I am going to make an assumption that 1 by RLCL is going to come after this. Okay, 1 by RLCL is the pole because of the output impedance, and we are saying that the pole occurs after the first pole, which is GM by CS. Now with this knowledge, we will try and find out the Bode plot. So first the DC gain here, I am going to take 20 log of this quantity. So 20 log mod of GMRL upon 1 plus GMRS. This is the DC gain. Now first we encounter 0. So the transfer functions start increasing with a slope of plus 20 decibels per decade. It keeps increasing till the point it encounters the pole. Now after it encounters the pole will try to decrease the transfer function at the rate of 20 decibels per decade. 0 will keep increasing it at the rate of plus 20 decibels per decade. So the growth due to the pole, the 0 will be cancelling out with the growth due to pole, and it will remain constant. The gain will remain constant. Now the important question is to find out what is this value here, what is this response, what is the magnitude level here. So there are two simple ways to find out the magnitude level. I'll discuss both. One is by circuit inspection. You look at the circuit and find it out. Other is by looking at the transfer function and finding out what is this value. So I'll use this simple expression. So let's say we have any term 1 plus S by omega Z or 1 plus S by omega P. For frequencies much greater than omega Z, I can ignore this term 1. So this term 1 plus S by omega Z can be approximated to S by omega Z. Same way, for frequencies much greater than omega P, I can approximate this term as S by omega P itself. I'll ignore the term 1 here. Okay, so I'll ignore this term and write this expression as S by omega P. So keeping that in mind, I'll use this equation to solve this, use this approach to solve this. And sorry, I forgot to mention this. If your S is much less than omega P, so which means you haven't approached the pole yet, then this term can be approximated to 1. So this term S by omega P will be much less than 1. If S is much less than omega P, then S by omega P is much less than 1. So then I can approximate this term to 1. So keeping that in mind, I can quickly analyze the circuit. So this term we have GMRL by 1 plus GMRS. Again, I can assume GMRS is much greater than 1. So I'll write this as GMRL upon GMRS. This multiplied by 1 plus SCSRS. Now remember, we have already crossed the 0. So at this point, we are way ahead of 0. way away from 0. So I can ignore 1 and write it as SRSCS divided by, first this term 1 plus SCLRL. We haven't approached the pole 1 by RLCL yet. Okay, so therefore SCLRL is much less than 1. We haven't approached 1 by RLCL yet. So I can ignore that term and simply write it as 1. The second term 1 plus SC by GM, because we have already closed this pole GM by CS, I will write it as SCS by GM. So now you can directly see these values. CS and RS will cancel out. GM and GM cancels out. Finally you are left with GMRL. Okay, that's the voltage gain you get here. So 20 log of GMRL will be this value. You can also get the same value by looking at the circuit intuitively and analyzing it. Okay, so you can get the same value by looking at the circuit. I'll use another simple approximation from a circuit point of view. It boils down to the same mathematically, but I mean you can choose whatever is convenient to you. If I have a resistor and capacitor in parallel, okay, if I have a resistor and capacitor in parallel, I can argue that if I have a resistor and capacitor in parallel, I can argue that after a frequency 1 by RC, this network is going to behave like a capacitor. So remember the impedance of a capacitor, so I will probably draw it somewhere here. So the impedance of a capacitor here decreases as a function of frequency, and the impedance of a resistor is constant as a function of frequency. At some value of omega, the resistive and capacitive impedances will become equal. After that, capacitive impedance will become much smaller than resistive impedance. Now if I put R and C in parallel, so whenever you have two elements in parallel, the one with the lower impedance will dictate the overall impedance of the network. So now in this region, if you see, the resistive impedance is much smaller than the capacitive impedance. Therefore, we can argue that in this region, this parallel RC network will behave like a resistor. So for frequencies much less than 1 by RC, a parallel RC will simply be equal to R. And for frequencies greater than 1 by RC, this circuit will behave like a capacitor. So we will keep this fact in mind and we will analyze the circuit keeping that in mind. So if you keep that in mind, this circuit here, we have already crossed 1 by RSCS. So which means this RS can be ignored. So this will look like a capacitor of value 1 by CS. And we haven't yet reached 1 by RLCL. So this will look like a resistor. This parallel RLCL will look like a resistor because we are far less than 1 by RLCL. We haven't reached it yet. So it will look like a resistor. Now this is the circuit we are left with. Now for this circuit, again, we can make another approximation, but I will probably explain it mathematically. This circuit gain can be written as GM by 1 plus GM into ZS of S. So ZS here is 1 by SCS, GM by SCS times RL. This is the gain for this. Now remember, our value of S right now, we are greater than GM by CS. We have crossed the pole frequency, which means GM by SCS here is much less than 1. So if I have taken S here, it will get much less than 1. So I can ignore this term. I am left with GMRL. So all we are saying is that this capacitance CS impedance is so small that we can treat it almost as signal ground, AC ground. Okay, we can treat it almost as an AC ground. So therefore, this will just reduce to a simple circuit common source amplifier without source degeneration and a load resistance RL. So the gain will be minus of GMRL. So here so far I have assumed R0 as infinity, but even if R0 is present, of course when we have source degeneration, the analysis becomes complicated. But if you don't have source degeneration, the analysis is simpler. Okay, I'll probably point out to a different lecture on how to consider R0 and analyze it if you have when you have source degeneration. But right now we'll try to gather some intuitions on differential amplifiers by making this approximation, especially R0 is infinity or R0 is much greater than all the impedance in the circuit. So now with this knowledge, I'll come back to the circuit. We found out the gain here. Now after 1 by RLCL, you will encounter another pole, so that will decay the response with a rate of minus 20 dB per decade. So now we have equipped the basic knowledge necessary to analyze differential pairs, a differential amplifier frequency response. I'll now just quickly take you through a general differential amplifier structure and show very briefly how to draw the differential half circuits. Okay, we'll now look at a general differential amplifier shown here. So here all these impedances can be both resistive and capacitive. So this can be both resistive and capacitive, and this can also be a resistive and capacitive impedance. How to draw the differential half circuits, and then in the next lecture I'll take some examples and try to find all the gains, differential mode, common mode gains, and all of that as a function of frequency. So before we draw differential half circuit, we said we have to draw this circuit in such a way so that I can draw an axis of symmetry. So I'm going to take this impedance Zt of t and model it as two identical impedances of value 2Zt in parallel. And this ZL of S, a single element, can be represented as two identical impedances of value ZL by 2 each, so that I will be able to draw a half circuit. So that's what I've done here. I have drawn the circuit in such a way such that I can draw an axis of symmetry around which the circuit looks like a mirror image of each other. Now there are two kinds of circuits we are going to draw. One is a differential half circuit, the other one is a common mode half circuit. To draw the differential half circuit, we said wherever this axis of symmetry intersects the circuit, that node will come to AC ground. So this is at AC ground, this node is at AC ground. So we said that's how the circuit reduces to. So this will be ZL by 2 and ZLS by 2. So then the differential half circuit, in the differential half circuit, this impedance Zt of S does not matter at all. This doesn't really figure in the differential half circuit because this node is at AC ground, the other node is at anyways at AC ground. I've used a word called differential ground to distinguish it from a conventional AC ground. So this node here is at AC ground. So the circuit reduces to something like this. So the gain for this circuit can be written as GM, that's the short circuit transconductance, times the output impedance, that will be ZL of S by 2 in parallel with Z of S. So that's your ADM for the circuit. If the impedances are frequency dependent, then you will get ADM also to be a function of frequency. The next step is to draw the common mode half circuit for this circuit. So to draw the common mode half circuit, again I'll start with the differential the circuit with showing the line of symmetry or the axis of symmetry. Now what did we say in case of common mode half circuit is that we are going to open circuit this line wherever it intersects the line of symmetry, we are going to open circuit this node, and this will be our half circuit. Now in this half circuit, if you see here, clearly this node is open, so there is no current flowing through this element ZL by 2. Therefore, in a common mode half circuit, when we are talking about a common mode half circuit for a differential circuit, this impedance which is going to be, this impedance is what we call as, I'm sorry I forgot to tell it in the beginning, this impedance which is in between the two nodes is what we refer to as a differential impedance. Okay, it's purely differential impedance. Even for example, I can call even ZFS also as a differential impedance, but this impedance is a purely differential impedance. It's connected between the two differential nodes. Okay, so this differential impedance will not matter in a common mode half circuit. So that's what I'm trying to explain through this circuit here. So this impedance will not matter. It can be resistor, capacitor, or a combination of resistor and capacitor. This impedance here will not appear in the common mode half circuit, especially an impedance connected between the two terminals here. Okay, of course, if let's say the impedance is slightly complicated, we connect some other impedance here, then yes, it will have some dependence because there is some path to the ground. But otherwise, if we connect a floating impedance between these two terminals, that will have no impact on the common mode gain of a circuit, because in common mode half circuit we are opening this node, so the current flowing through this is 0, so the voltage across this is 0, so I can simply ignore that and show the common mode half circuit which is shown here. Now the common mode half circuit, from this we can write the gain as the short circuit transconductance. So again GCM of S is the common mode short circuit transconductance. That will be very different from differential mode short circuit transconductance. It can be very different from differential mode transconductance. For some circuits it can be same, but for some circuits it can be very different. The common mode short circuit transconductance and the differential mode short circuit transconductance can be different. Now we have ZCM of S times ZOCM of S. Here ZOCM of S is the output common mode impedance, for the output impedance for common mode inputs. So that can also be very different from the Z out of S in a differential circuit. It can be same, but it can be different as well. Now GCM of S, the common mode circuit, the output impedance, common mode short circuit transconductance can be expressed for this circuit. This is a simple source degenerated MOS amplifier as GM by 1 plus 2 GM into ZT of S. Because this impedance is 2 ZT of S, you will get GM by 1 plus 2 GM into ZT of S times Z of S. ZOCM of S will be your output common mode impedance. But for in this circuit, ZOCM of S happens to be Z of S here. So in the next lecture, I am going to take up a few circuits and apply all these results and try to find out the frequency response for differential amplifier. So we will find ACM of S, ADM of S and ACM, DM and CMRR of S as a function of frequency. Thank you.